Alright, hell yeah. So this is a quick little video about a physics concept that I was just thinking about. You know what I mean? I was thinking about a mass rotating around a circle. You know what I mean? So whether it's around a stick, and we have a change in the direction. And I couldn't quantify why a change in direction is equal to acceleration. And then I was just thinking about it a little bit more. Like, what is, you know what I mean? Like, acceleration is going to be a change in velocity. And so, in this case, it doesn't seem like we have a change in velocity at all because the velocity is going to be constant. We can have a mass going around a circular area, and it's still accelerating. And it still requires a force to do that. Either a string has to be in tension, or if it's a racetrack, you know what I mean, the wall is getting compressed, up against the earth and stuff like that. And so, but it just doesn't feel like there's an acceleration because this thing doesn't change velocity. So how do we quantify this? Well, let's take a simple example of a mass is falling, and then we get down here to this height, and then we have a spring to catch it. You know what I mean? So we have a spring to catch it, and maybe this spring has a recess. So by the time this ore just is hella long or whatever, and it's right there, but as this mass falls, it's going to compress the spring, and then this is going to be the position of that mass after it compresses the spring. We're going to say that, and let's just, I don't know, let's get rid of gravity. And this would just be a horizontal track. So I'm just going to say this is an overhead view. This thing has, a frictionless disc. This is an air hockey table. This is a puck meeting against a wall. I think, yeah, so we got rid of gravity. This is just a big air hockey table. Here's the air holes. These are the pucks. So now we can see that this mass is coming in, and it has velocity, so we're going to give it a constant velocity. The second it hits this spring, it's going to have a force. That means, F equals ma. If we have a net force in that direction, we're going to have an acceleration. Alright, hell yeah. Sorry about that. Camera ran out of juice. Alright, so sweet. And we can kind of just get to it. So, hell yeah. We can look at this as vectors. This has a velocity vector that way. I can totally tell it's going to have a change in velocity. Therefore, acceleration. Cool. And if we look at this as a vector, this vector has an arrow that way. And that vector gets diminished as it's hitting the spring. It gets smaller and smaller, and then we have zero velocity. So I definitely get that. This has to go to zero. So what's happening in this, from this example, is we're just changing this velocity arrow to this direction. So let's reduce this a little bit and pick up that arrow. Reduce this a little bit more and pick up that arrow. And then let's get rid of that. And so that's what we're doing when we go around a curve. You know what I mean? Hey, this vector for sure gets reduced as we take this block and go around like a curve like this. And so, you know what I mean? Just by the nature of a curve, even if you don't even understand what's going on, the second we leave this curve going this way, you know what I mean? Do we have any more velocity in that direction? No. Hell no. And if we came in with a velocity right here, and then this brings up another important point. And this is kind of an interesting thing. I can drop something off a cliff, and it can have instantaneous acceleration. I can hold it by a string, and then scissors, you know what I mean, through that string, and it can have an instantaneous acceleration. That's fine. What things can't have is an instantaneous instantaneous change in velocity. You know what I mean? So you can have you can go from zero acceleration to instantaneously having 10 meters per second, which is a change in velocity of 10 meters per second, but it's in a change in time. What you can't have is this change in velocity in an instant. You can't just be like, at this moment, I went from a velocity of 10 meters per second to 20. You know what I mean? You just can't have that. You can, but it requires an infinite amount of energy because your acceleration, You did have a change in velocity of 10, but your time just went to beyond 0, beyond differential equation 0, and this becomes infinity. So if you can provide an acceleration of infinity, and that's where we have F equals ma. If you have infinite acceleration, it took infinite force and more just general, you know what I mean, energy is the word there. It takes an infinite amount of energy for something to change its velocity instantaneously. Okay, but the general gist of this video is to kind of just show how these, you know what I mean, this had a velocity vector this way, and now it has a velocity vector this way, and no longer has velocity that way. When it's at 45, you know what I mean, when this thing's kind of doing this, hey, maybe it's equal. We have, I mean, the velocity vector down is equal to the velocity vector over. We still, in this whole problem, we're still saying that it has a constant tangential velocity of v. And so if this is v, then this is going to be 0.707 v. That's a great way to look at it because it's 70% of v, and that's 1 divided by the square root of 2. It's also 2 divided by the, square root 2 divided by 2. All the same things mean, you know what I mean, 1.1414 divided by 2. Booyah. 0.707. And hell yeah, you can see how that's divided by 2. Anyway, so hell yeah. And then another way to look at this is just like, hey, if I had, yeah, this is kind of cool. So I'm going to have a spring on this, and it's up against this wall. And it's all sprung. It's like really tightly sprung. And then I have a button. And cool, I haven't pushed the button yet. We have some velocity this way. At this point, that is when I'm going to push the button on this tightly wound spring. So I'm going to push that button, and guess what this button's going to do? So in this scenario, the button is going to take this block and push it to all these points. You know what I mean? So when it gets to here, this spring is going to push it to there. By the time it gets to here, this spring is going to push it to there, and it finally pushed it to that location. The spring hit a stop. It didn't have any farther to go, and now we have imparted this velocity into this. Now, at the same time, this thing has to have a spring, you know what I mean? Let's say this thing has a spring this way that's the same height as this. So there you go. So you have a spring that's sprung, a spring that's ready to be springed, and as this goes to here, this spring hits the ground and starts to activate. And so it reduces its velocity. So, and then as it's getting pushed this way, so now, sorry the picture is overwhelming, but I just thought this was a very good visual of a block going around a corner. You can visualize as two vectors. One, a spring slowing it down this way, and then another having the spring tightly sprung, and then having a button that you push at some point to have that spring go that, you know what I mean, to undo itself. And, sorry about that. And then it pushes it, you know, into an arc. And then that would be a way to show, and it doesn't have to be an arc. It's just like, how do you quantify a circle from, and I think we did it, you know what I mean? We're saying we're slowing down in one direction and killing that velocity over a period of time. And it just happens that a circle will have a constant. That was the interesting thing, is like the acceleration, I'll have to think about that. It's not quite right. The overall acceleration of the system is a constant. So if you have a constant velocity going around a constant diameter circle, like, don't you have a constant acceleration because you have a constant tension? A constant force, F equals ma, gives a constant acceleration. But from this diagram, if we're I guess these two things are not the same, because we're not coming in with a straight run. We're just always in a curve. So that's kind of interesting. But if we're in a curve, we're always at the tangent as well. So it'd be the same thing as this coming in and then slowly slowing down. So this acceleration right here is going to be slow, and then this acceleration right there is going to be slow. And then, yeah, I don't know. It's probably at every point you're going to reset that. And so I don't have a good enough answer for that. All I wanted to know was just like, hey, is it vectors? You know what I mean? By changing direction, is one of this is the deal. If I have a velocity and I change direction but my velocity doesn't change, why is there an acceleration? Well, it's because I'm still having that same velocity. Having that same velocity this way is a vector that way. If I have that same velocity that way, it's not so much this way. So we do have a change in the velocity that way, therefore acceleration. We didn't have any change, we didn't have any velocity that way, and now you're saying you have a little piece that way. So we have an acceleration that way. And accelerations are also vectors. You know what I mean? So, hey, if I did this and then went that, this acceleration slowed down, this acceleration picked up, and maybe we have a resultant. And that's the interesting thing. It never got taught to me. You know, I don't know. There's so many ways to teach things. It's just kind of fascinating that, yes, acceleration is a vector. And it's really useful to be like, what is a vector and what's not? And then figure out what's not a vector. Material mechanics is the best one because you can take a block and you can put a shear stress on it. These are a function of the area. You know what I mean? If your area is all the same, hell yeah, you're probably going to be good to go. But if you have something like this, you cut that at an angle, you know what I mean? And then here's your stress, you know what I mean? And then here's your stress. These are tensors. They're not vectors. And then you're going to have some sort of sideways stress and a normal stress. So these do not represent a free body diagram. The numbers do not add like vectors. All right, we're done with this video. I just wanted to kind of wrap my head around a mass going around in a circle. It's changing direction, I get that. Why is a change in direction associated with acceleration? Because if you have a change, and this is a very specific case of a change in direction where the velocity doesn't change. I'm going this way with the velocity, now I'm going that way with the velocity. Hey, this vector shortened, and we actually picked up some vector here. We have an acceleration that way. We have an acceleration slowing this one down. Booyah.